Over the last few months, I built an end-to-end video streaming solution from encoding to delivery because every other option was either broken, overpriced, or both. I had a client that was forced to switch video streaming providers because their existing solution announced that they would be shutting down. The suggested replacement tanked performance so badly, videos stopped playing, Chromecast support was completely broken, and users were unsurprisingly upset. Rather than gamble on a new provider, they decided to cut down their reliance on third-party systems entirely and asked me to build something custom. Along the way, I had to untangle a video library shaped by years of shifting file naming conventions and write software to match everything back up. The real challenge, though, was avoiding database corruption, because a run of bad matches could poison the entire system, and pulling that apart again would be a full-blown forensic nightmare. What started as a quick workaround turned into a crash course for everything that could go wrong, and a much bigger project than I ever expected. For those unfamiliar with the channel, my main development project is an Unreal Engine stealth combat experience. But due to urgencies at work and a really chaotic house move, I haven't made a lot of progress in that department lately. But to those who have been following the effort for the last couple of years, please bear with me. I haven't abandoned anything, and I expect life to calm down again pretty soon. So if you're not already, get subscribed to follow the progress on that one. For now though, let's dig into this video streaming solution. The first real decision was picking a programming language for the backend, the part of the system that does all of the real work. I chose a language called Go. It was created at Google by a team of veteran engineers, most notably Rob Pike, who helped design the Unix operating system and the C programming language. Go is designed for fast, scalable systems that need to run a lot of tasks at once, quickly, reliably, and under heavy load. Another word for this is concurrency. When you're dealing with 4K video uploads, simultaneous encodes, and real-time status updates, predictability matters, and Go handles this out of the box. I did look at a few other options. Python, Node.js, and Rust were all candidates, but Go hit a strategic middle ground between performance and simplicity that was really attractive. Once I settled on Go, I started building. First was a server that could take video files, hand them off to FFmpeg, and return something streamable. If you've never heard of FFmpeg, you've definitely used it. It's the back-end workhorse behind most video software. Compressing, converting, trimming, packaging. YouTube uses it, OBS uses it, your favorite screen recorder probably uses it too. Next, I threw together a simple uploader website. Just a simple drag and drop web page to get videos into the pipeline. The architecture looks something like this. The upload comes in, FFmpeg processes it, out comes a clean, streamable video. That was the plan anyways. The first issue I encountered was uploading large video files over a typical internet connection. To avoid crashes or timeouts, the safest approach is to break the file up into smaller pieces and sending them to the server one chunk at a time. In theory, that's pretty straightforward, but in practice, keeping all those chunks in order, confirming they arrived intact, and stitching them back together again can be a little tricky. Then I started running into server timeouts, basically the point where it just gives up and assumes you've disappeared. Uploading a multi-gig file from a hotel lobby or a spotty home internet connection is an easy way to hit that ceiling, so I needed something dynamic that could adjust based on the file size. And then finally, I needed a way to communicate job handling. The server could process multiple videos at once, but to the end user, it just looked like a black box. No progress indicators, no job status, no sense of what their upload was doing. So I created a job queue, a way to track every file in the system, show which ones were uploading, processing, failed, etc. Basically a status dashboard that made the whole thing work for the folks that I was building it for. But all of that was nothing compared to the real problem. The client's entire library was built on Microsoft's Smooth Streaming, a proprietary format whose support with modern devices is steadily dropping. Because of this issue, and a broader desire to reclaim more direct authority over their tech stack, we made the call to move everything off of Azure's cloud service and onto dedicated storage. That left us with the biggest decision yet. Option A was keep the original smooth streaming files and convert them on the fly for modern devices. This is pretty much how Azure's suggested partner operated, the one that we had tons of problems with. Or option B, re-encode every video into a universally compatible format, even if it meant reprocessing years of content. Option A was clever and flexible, but it felt more like a moving target and required more maintenance. Option B was slower and dumber, but predictable. No real-time processing, just clean, pre-encoded, stream-ready video. So we went with the latter. Short-term pain for longer-term simplicity. Turns out, re-encoding thousands of videos takes time, 4 months to be exact. But it was mostly automated. Outside of a few edge case hiccups, it was rolling night and day on its own. At this point, I really thought I was all the way out of the woods. But then the biggest curveball of the process hit me. You see, each folder on both the old and new storage servers uses a long, randomly generated string of letters and numbers to avoid naming collisions. The new storage server was supposed to be a straight copy of all of the files, so I dangerously assumed the folder names would be the same in both systems, which would have made updating each video a breeze once the re-encode process finished. Imagine the drop in my stomach when I discovered that I was completely wrong. Every migrated folder had a different ID than its counterpart from the old system. This meant I had to craft a completely custom approach to figure out which files on the new storage server matched up with videos currently playing on the website. The first obvious step was looking at file names. I could index every file on the new server and simply find the existing video with the matching name. And that actually worked for a good many of them. But the server was also littered with files that shared the same name. So I needed a different way to match those up outside of manually watching them and updating database entries one at a time. For those, I pulled the video's stream manifest to get its duration. If the duration of the existing video on the site matched the one on the new server, I could reliably know which one to replace. But even that didn't cover everything. Some duplicates had the same name and duration. For example, if someone tweeted the credits on a film, that wouldn't exactly change its runtime. And if they uploaded the new version with the same file name as the original, we're screwed. And because all of these files have been migrated, every creation date was just the date of the migration. So even a simple which one is newer approach was too risky. So painfully, those had to be re-encoded again, using the highest res version from the old streaming manifest. Not elegant, but better than data corruption. And suddenly, somehow, after months of watching a slow re-encode process, edge case nightmares, and comparing folder names, everything was actually working. Chromecast was playing, the TV apps all fell in line, no buffering, and no angry customers. Now we're focused on cleaning up. Because every video points to a new location, we can run a job to delete anything from the storage server that isn't tied to a database entry, because we know for sure that video isn't in use. So it's not $1 billion streaming pipeline, but it's fast, it's cheap, and the client completely owns it. Since the initial build-out, because I worked with other team members that handle the database and website-specific API endpoints, I felt like I needed some personal experience with those pieces that I didn't really get to touch. So in my free time, I've been rebuilding every bit of the video encode process from the ground up, but in tandem with my own database approach to storing video objects, and how those relate to other data structures like categories or series, and even an approach to users that can authenticate and watch the uploaded content. So if you need some video streaming consulting or just help with your video streaming website, you can email me from my website at baker.dev or from the links section on my YouTube channel. For now, though, I need to get back to Unreal Engine. I have a lot of time to make up for in that project. If you're interested in more development content like this, be sure to get subscribed, and I should have a new devlog for that project dropping soon.